So, once again, if you sound hears my students talking, it's okay. They're having lunch. They're allowed to talk. Hopefully, my voice will rise in educational glory above theirs. So, no air resistance. No air resistance. This problem is good because it illustrates the difference between a situation where mechanical energy is conserved, beginning and final mechanical energies are equal, and where it's not conserved. Because if we have air resistance, then mechanical energy initial will not equal the mechanical energy final. In other words, there will be a change in mechanical energy. So, starting with the first one, they give us an initial velocity, I believe. And if we call, if we call the initial height 0, then at this beginning, we know that the mechanical energy, I'm going to write this over here. So we'll do this whole thing in this purplish color, and we will call it no air resistance. So in that circumstance, the initial height is 0. The initial velocity they give us is 24.5 meters per second. Of course, the mass of this thing is 0.768 kilograms. So the initial mechanical energy will equal the initial gravitational potential energy. I should just say potential because there could be a spring or something involved, but in this case there isn't. So plus the initial kinetic energy. Well, since we're starting at ground level, this will be 0. And the initial mechanical energy is all going to be in the form of kinetic. 1/2 m, which is 0.768 kilograms, times v squared, 24.5 meters per second squared. So a few buttons on the calculator later, and I got 768 times 24.5 squared equals, I get about 230.5 joules worth of mechanical energy at the start. Now, for that first situation though, whatever the mechanical energy is here at the start is the mechanical energy anywhere along this path, including up here where they're concerned about at its highest point. But it would be the same mechanical energy here, as here, doesn't matter where, if there's no air resistance. Well, what about that highest point? What do we know? At this highest point, all of the energy will be in the form of potential, and I know this because it stops at its highest point, and therefore its final kinetic energy is 0. So all of that mechanical energy that we already know is in the form of potential energy at the top because it stops. So let's go down and figure out the height. That means mechanical energy initial equals mechanical energy final, which in this case, since it stops at the highest point, is all equal to potential energy. So I have 230.5 joules equals mgh, and I know m and I know g, so I solve for h. That's going to give me, let's see, 230.5 joules equals, notice, really I could cancel out the masses at this point, but you notice they would have shown up on both sides if you look at it a little bit. 0.768, I'll stick with it though. 0.768 times 9.8 times nothing. There we go. So I got equals 7.526 h. Divide both sides by that. And it should go to a height of 30.6 meters. Let's see if, by the way, got to check to see if you're getting a quality education, folks. Let's see. Oh, yeah, there we go. Yep, you're okay. You can't fire me yet. There it is. Okay. But I can't use the highlighter apparently. Okay, so now about the second case. So let's go ahead and get rid of this here. In blue, we're going to look at this case. Here, I'm going to start with the same mechanical energy, same velocity at the beginning, but at the end, I'm not going to have that mechanical energy, because here it still stops. Mechanical energy final is going to be the potential energy, which I actually know the height, so I can figure that out. But it still stops at this point, at its highest point, so it doesn't have any kinetic. And certainly, mgh of whatever the mass is, times g times 8.15 is not going to be nearly as much energy as it was all the way up here. I think we would agree with that. So, in this case, with air resistance, I know that the initial mechanical energy would be the same. So it's still going to be the 230.5 joules. Still throw it at the same speed. But because air resistance acts, it doesn't go as high. In fact, they tell me how high it goes. So at the final point, remember, there's no kinetic energy. All of the energy will be, because it stops, in form of mgh. And in this situation, that final mechanical energy is 0.768 kilograms. He says, trying to remember, let's make sure that's right. Come on. There. Yes. Times 9.8 times 8.15, I believe it was. Yeah. So I can figure out the final mechanical energy. $61.3 or so. Now, what we know in situations like this is that that change in mechanical energy is equal to the work done by any external or non-conservative forces. In this case, there is only one of them, and that is the work done by air resistance. So since it wasn't conserved and there was a change, that change came from whatever work was done by air resistance. Well, I can figure that out pretty straightforwardly. By the way, there's lots of ways to look at this relationship. But in this case, I think this works out the best. That means the final mechanical energy minus the original has to equal the work done by the air resistance. So that's 230.5 joules minus 61.3 joules. And that means it's the work done by air resistance is going to be 169.2 joules, rounding. I may not be what they asked us, because that's just the work done. I'm guessing here, they might ask me for the actual force, because I think we can figure out the distance. If it moved up 8.15 meters, that would be the displacement of the object. So I'll bet you they ask you for the force. Let's go look and see. I really don't know. I can't recall. Yep. What's the magnitude of the average force due to air resistance? The force would actually decrease as it slowed down. That's why they say average. But we can treat it as an average for now, and that's fine. So that height also becomes the displacement. And the whole time that it's doing work, and by the way, it should come out to be negative, right? No, we're good. Oh, it should be negative, so let me make sure I got this right. Final minus initial. See how I messed that up? We got to switch these two. This should have come out to be negative. That should go here, and this should go here. I should actually have a negative. Here's how I know I have a negative. as that thing moves upwards, this displacement is this way, the force of air resistance is this way, it's got to be negative work. And that's why I realized I must have switched these two, and in fact I have. But it's okay, we'll correct that now and make it negative. So I have work equals force times distance. I have the work done is negative 169.2 joules. The force I'm looking for, it's actually an average force. And the distance is the 8.15 meters that it moves in that time. So I have that divided by 8.15. And the average force of air resistance comes out to be about 20.8 newtons, negative 20.8, downward in this case, if we took up to be positive. There we go. See, you're getting your money's worth of education here, folks. I'm just saying. All right, that's it.